All right, let's start the video 2, and then we are going to talk about your next assignment, guys. This is what we're going to look at. So first, before we start the lecture, I'll talk about your next assignment because you need to understand the context. Basically, it's about calculating means and expectations, and that's it. Okay, so you'll basically have to do that within the context of a linear model. So you have a simple linear model. Okay, I mean, it's simple means that basically there's just one predictor, so you see what it would be. Okay, so A and B are the parameters, as you might guess. All right, so then you have X, which is some sort of a predictor, which is random. So it can be random, but it is a random variable, and we are basically going to look at that one. And Y is also going to be random, because since X is random, then of course, and then epsilon will be random, then of course the combination of the two is going to be also random. So I didn't basically wrote it down explicitly that the response is going to be random, but I think it should be clear then. All right, and then you have the noise, which is basically, you know, kind of causing some sort of turbulence regarding the linear relationship or a possible linear relationship between X and Y. So this is basically how the model works. Okay, and then again, as I mentioned before, since the noise is random as well as basically the predictor, as we assume in this case, then the response will be also random, but it should be clear now. All right, okay, A and B are some sort of parameters. You know, you don't need to estimate them. This is not what this is going to be about. We have basically two assumptions regarding the conditional expectation of the noise. So we're going to assume that the conditional expectation of the noise is 0 given the predictor. All right, so given the predictor, the conditional expectation is going to be 0, as well as the conditional variance. Now the conditional variance is not going to be 0, so the conditional variance is going to be some sort of a constant. Okay, so keep in mind it's sigma squared, but it's not necessarily normal. So you're not supposed to think that just because you see sigma squared, it kind of causes some sort of confusion most of the time, because people think that this might be basically related to the normal distribution. It's not. Okay, so just, I have to call it somehow. Okay, and then basically I would call it sigma squared. Okay, so this is actually another parameter from the model, but that's what the conditional variance would be. Okay, so sigma squared, and again sigma is just basically a positive constant. All right, and you need to understand that basically the predictor is not specific. So when you calculate stuff, again, so regarding expectations as well as variances, okay, that's what you need to gonna do. Okay, do not assume that the predictor is specific when you consider those moments. All right, so again, I'm talking about conditional moments basically. I mean, the variance is not the second moment, but it requires a second moment at least. So this is something that you would need to understand here. Okay, so do not assume that X is specific. What does that mean? Do not assume that it's a constant. So don't assume that there are observations there in this regard. Okay, because if you do, then you're going to get different expressions, and I need to penalize you for that. So this is not something that you would need to consider. Okay, keep in mind, guys, that conditional expectations as well as conditional variances can be random. In this case, they are not. Okay, so clearly they are not, because they are constants. Okay, but in general they can be, and I was showing you that last week. So last week you saw, I think it was lecture 2, where you had conditional expectations, at least conditional expectations basically being random, and that is also true for the conditional variance as well. Okay, so now, all right, so I want you to basically to address, you need to also assume that, when you look at these expressions, you need to assume that the expectation as well as the variance of the predictor is going to be finite. Now, of course, if the second moment is finite, you should understand that since the variance of the predictor equals the expectation of the square minus the square of the expectation, now if basically this is finite and that is finite, this concludes basically that the variance is also finite. So regarding the variance, it would be finite. And this means that you can, since it's well-defined, so well-defined is basically, it means that, it can be specified explicitly. So whatever the variance would be, it should be fixed, at this point, okay? So then you would need to assume that these are things that you can use. So whatever expressions you have, okay, as the final result regarding your assignment, you can use the expectation of X as well as the variance of X in it. Okay, because this is well defined, so that means that it's there, okay, and it's going to be finite, so that means that there is no such thing as limits and all that stuff regarding it. All right, is it clear? Okay, so well defined means it, for example, it is equal to 5 or something, whatever. No, the predictor would be, or the expectation of the predictor is. It doesn't really matter. Is that clear, guys, so far? And I basically would need to address that. So these are things that you can use as your final result. Okay, so whatever comes out regarding expectations and variances, this is something that you can give as a result. Okay, so whenever you see the second moment or maybe the first, okay, so that's that. Now you need to calculate some stuff, and you need to basically address a lot of things using two major, actually it's four. So you use the law of iterated expectations. Okay, so let me basically address what the law of iterated expectation is. The law of iterated expectation claims that the unconditional expectation of a random variable, let's call it y. So I don't want to confuse you, because it's always, most of the time, it's always going to be the predictor, which is going to be the condition. But let's say the conditional expectation of y is going to be equal to the expectation of the conditional expectation. So you have the expectation of the conditional expectation. This is what the law of iterated expectations would claim. Okay, and you just simply assume that it is true. So you don't need to prove that, none of that stuff. This is the law of iterated expectations. You'll find it on basically on the slide here for the second part of this lecture. And you're also going to have the law of total variance. The law of total variance regarding the unconditional variance of a random variable is going to be basically, you know, a sum of two other expressions. The first is going to be the variance of the conditional expectation. So that's basically number one. As you see, the variance, and in this expression, the conditional expectation can be random. I'm not saying it is, but it can be random. Okay, if it's random, then you need to calculate basically its variance directly. If it's a constant, then the variance of a constant is going to be 0. Okay, so that's something that you should know. Okay, so whatever the variance of a constant would be, that is 0, but it's not a constant in general. Then plus the expectation of the conditional variance. Actually, it's the other way around. Okay, so it's expressed basically differently, but I'm going to write it like this, so because I was starting like that. So basically, it's actually the expectation of the conditional variance, and then you have plus the variance of the conditional expectations. And what you also need, so what I mean by basically by further properties, I mean expectations and variance of sums. Okay, so whatever that are. Okay, so you might remember the variance of x plus y is blah blah blah, and the expectation of x plus y is blah blah blah. So expectation of a sum is, you know, sum of the expectations. Now the variance of a sum is not the sum of the variance in general, you know that. So I will basically, you need to address that as well. And then you would also need to talk about what expectations and variances of linear transformations are. So these are the things that basically it's listed in the second lecture. We have talked about them, and then you can basically, you just need to use them. Okay, but you might remember that the expectation of a linear transformation is the linear transformation of the expectation. All right, so these are the things that we talked about actually, so last week, and you need to put those together to find these expressions, and for each you're going to get 10%. So if you basically need to address the unconditional expectation of some noise, that's something that you need to address. Okay, so I want you to find it out basically. But just to remind you, I mean, for me, it's not the result that is important. Now this time is going to be, you know, the calculation, which is important. So you need to show, and then let me tell you something, this is going to be 0 also. Okay, so both the unconditional as well as the conditional expectation of the noise is going to be 0, but I want you to show that. So I want you to basically to address this issue. Okay, so it's not about the result which I'm interested in this time. So keep in mind that could not be enough. I'm interested in basically, you know, you explaining why it is 0. So actually I could have been also doing that as well. Okay, now you would need to also address the unconditional variance, and you might suggest, I mean, you might know how to. Okay, so what is the unconditional variance of the noise? Following basically your assumptions, or from your assumptions basically, you know, how would you get that? You're going to get 10% on that as well. Now I want also to calculate the conditional expectation of a product of basically the noise and the predictor. Okay, so that's basically what is going to be. So that's going to be the third part. You're going to get 10% from that. Now, based on that, you need to calculate the unconditional expectation of a product. Again, so these from the 4 things that I was giving you. Okay, law of total variance, law of iterated expectations, expectations and sums of linear transformations, and expectations Yeah, and sums of linear, no, expectation of a linear transformation as well as expectation of a sum. Then you have also the variance of a linear transformation, the variance of a sum. These are basically just the 4 things that you would need, and then you would need to set that together. Now from that, it's easy basically to address what the covariance will be. So let me tell you something that's going to be also 0 as well. So this means that the predictor is not going to be correlated with the noise. And that is very interesting, guys, because this is not an assumption we have. This is basically a consequence from the 2 assumptions regarding the conditional expectation and the conditional variance of the noise. Understand what I'm saying? So this is quite extraordinary. That's why it makes it so fascinating regarding this issue. So again, that will be a consequence, and you'll find that the noise is not going to be correlated with the predictor because the covariance is going to be 0. Okay, and I want you to show that. So just by addressing conditional expectation and conditional variance of the noise given the predictor, you'll find that the correlation will be 0, and the unconditional correlation, by the way. So again, because covariance involves also some sort of moments, right? So you'll find that basically these 2 things will be uncorrelated. You're going to learn a lot, by the way, from this context. All right, now the second half is going to be a little bit more difficult, so I'm not going to address those because then you have much more work to do. So if you take time, you need to maybe 30 minutes or probably an hour to solve this. So again, the second half is a little bit more, and it's not complicated, so it's the same, basically the same principle that you need to address, but it's going to take much more time. So you have basically the unconditional expectation of the response, that's and for that you need to have the conditional expectation first regarding the law of iterated expectations. Okay, so that's something that you need to address first. Now regarding the unconditional variance, you would need to solve this basically from the law of total variance, and then you have also expressions that this is basically required to address. So again, I want you to find that out what it's going to be. Okay, you're going to be surprised, by the way. And then you also need to address what is the correlation between the predictor and the response. There's going to be some correlation, because if there is none, then you would not be able to establish some sort of linear relationship between the 2. Okay, so the correlation this time will not be 0, and I want you to figure out what it is. All right, so now, basically in the 9th case, I want you to calculate the square of the correlation. Okay, whatever that is. Okay, so not the rho is a correlation, the theoretical correlation. I want you to take its square, because I want you to address something. I want you to compare that to basically to this expression, the variance of the conditional expectation divided by the total variance. You can also say that this is the variance of y is a total variance. And I want you to compare those 2. But again, you don't need to. So if you want to basically get 100%, this is what it's going to be. But if you, let's say, fail 1 or 2, okay, you can upgrade your assignment, but you could not get more than 100%. So I will give you an option, which is basically the 11th. So compare those 2. And of course, you need to have those. Okay, so, and I want you to calculate basically, I want you to give me the steps involved. Okay, so it's not going to be basically that, just you dropping the final result, because that's not going to be sufficient for me. All right, I want you to basically to explain why is, these are going to be equal, by the way. So I can tell you something, and the question is, what has that to do with basically with our assumptions, or what it is about, why they are equal, and this and that. So you were showing here something regarding basically these 2, and I want you to address what you have shown. Okay, so basically, what does it tell you explicitly? All right, but again, that's just a bonus. So if you skip that one, you can have 100%, but you cannot get above 100%. So, but if you maybe fail 1 or 2, then this is something that you would need to have. All right, so these are the things that I want you to address. And maybe it takes an hour or something. Okay, so it's not going to be difficult, just to be honest, but you're going to learn a lot, and I want you to basically go through that approach as well, and then you'll see what these results are. Now, also you can use the following things, which we haven't addressed: the conditional expectation of a random variable. So it's not necessarily just the predictor, guys, okay? It can be the predictor, but most of the time the condition will be related to the predictor itself. The conditional expectation of a random variable with itself is always going to be equal to 1, and the conditional variance of a random variable with its, or given itself, right, is going to be 0, because then it has no variance. So if the random variable is given already, whatever that is, okay, then it has no variance, all right? But that's something that you can use in this context, okay? So you can basically build that into. Of course, what I forgot to mention is that the expectation of a constant is a constant itself, and the variance of a constant is 0, okay? So if it's a constant, then it has no variance. I mean, you can say that the variance is 0, but again, that's quite, you know, the same, all right? Now, also, there is another, theorem, let's say, that is needed here during that consideration, because I haven't addressed what the covariance of sums would be, okay? So if, let's say, A, B, and C are pairwise uncorrelated, and you want to address what the covariance of the two sums would be, so A and B and A and C, all right? This is something that I'm also going to use frequently in time series, because as you see, they are pairwise uncorrelated. What does that mean, actually? So that means that the covariance of A and B is 0, the covariance of B and C is 0, all right, and the covariance of A and C, this is missing. You know, that combination is 0. Pairwise uncorrelated. You understand what I'm saying? So if you basically address the covariance of their sum, then you need to know that only those expressions matter that do overlap with each other. So what could be the intersection of the sum, let's say. And only those matter, because everything else is going to be just canceled regarding correlations, all right? So there is no such thing as the intersection of the sum, but if I say, what's the intersection of these two sums? I mean, basically, the sum ends that they have in common, okay? Because everything else is going to be uncorrelated. Now, if this is the case, all right, so you have some components in both which are identical between the two, all right, then this is just going to be the variance of the component that they have in common. Simple as. Okay, so I call this the intersection. Okay, so let's say the intersection of A plus B and A plus C is, let's say, A, and then the covariance of the sum of the two sums is just going to be, they're just degenerating to the variance. And that makes sense, guys. Okay, so when you basically look at that, okay, you add the components that do overlap with each other, because these are the only components that do correlate with each other, and the correlation basically is going to be identical to the variable. I mean, if I say correlation, okay, I actually mean covariance, but covariance of basically of a random variable with itself is just going to be the random variable. All right, so you can use that theorem. You don't need to prove that, by the way. You can address it, but you don't need to. Is it clear, guys? All right, so these are the things that you can use. And so that's that. And then please notice that it's not enough for me that you just drop, the final results, because I could give you the final results already. So you could basically, but I don't want you to feel distracted and stuff, so you might not get there and whatnot. So I want to basically consider 1 or 2 partial results, especially the ones where you got work to do again. So for the second half, you have more work to do than as for the first half. The first half is quite easy, that maybe just requires 10 minutes, but the second half might require, let's say, half an hour or so. But again, it doesn't matter. So I'm going to be giving each of these expressions equal weight. Okay, so you upgrade your assignment with the easy ones. Anyways, guys, so please provide basically the calculation. You don't need to comment those. So if I read your stuff, I should basically be able to understand how to come up with the idea, but you don't need to explain it, of course. Okay, so some of you guys were providing me comments, which is fine, but in this case, you don't need to. So just, but I need to have the steps. So even if you skip 1 or 2, I want to basically, I want you to address those. So don't skip the steps, right, that are involved. Just write them down, and then basically that's it. All right. Now the deadline is going to be next Friday, as usual. Okay. So if each time I will publish an assignment, I'm also saying it's going to be Friday, so you can take the weekends off. All right. But that's basically it. All right. So Friday at 11 p.m. Are there any questions related to that, guys? Is it clear what you have to do? So again, you don't need to basically to make assumptions regarding the random variables. Okay, so just basically one exception though, that expectation and variance unconditionals of the predictor is well defined, or are well defined and are finite. That's it. Okay. So yeah, it's not difficult, guys. So it might look as such, but it's not difficult. This is very important, and you're going to learn a lot by this assignment, especially when you have econometrics, right? So maybe there's a lecture in econometrics explicitly. I mean, we also doing econometrics, but related to time series. But even in time series, we have the same tools. So we have expectations, variances, conditional variance, unconditional variance, conditional expectation, unconditional expectation. So it's always going to be the same tools, but within a different context. Next week, we're going to start with time series, by the way. So, but I want you to have these blocks handy. All right. Okay. So this is how it works. And yeah, so please submit. I'm expecting your submissions. And yeah. So, all right. Then I'm going to start with the presentation here of today's lecture. So, okay, so this is going to be lecture 4. I'm going to talk about basically topics first. So we're going to look at the linear model just as basically in the context of the second assignment. I'm going to basically give you an idea how to calculate the standard error of regression within a simple linear regression model, but this is also true for the multiple regression model. And I'm going to address basically the t-test here, so testing the significance of a predictor, and this is basically the most common t-test, but I'm going to also look at other test statistics or other tests as well. Okay, now the simple linear regression model, just as I mentioned before, within the context here of the second assignment, is going to look like this in this context. Okay, so you have a random predictor, you have a random noise, and then of course, you know, the response will be also random. So this is basically how the generalization, or in this basically the context that I'm in, works. Okay, so I'm just basically explaining the same things. You saw this when I was introducing to the second assignment, so I don't need to talk about that again. Okay, so this is the context, guys. Now, within basically, I mean, you could also break it down for single observation. So you have basically the assumption here that for every observation, there is a corresponding random variable. I mean, there are corresponding random variables generating those observations, both for the predictor as well as the response. Okay, you can also say that you have basically, you know, hidden observations basically for the noise, but the observations of the noise are not going to be observable in general, except for maybe if you are the one, you know, trying to simulate the data. So if you're simulating the data, then you do have the observations of the noise, but in general, it's not going to be observable. What is observable or what will be observable are going to be observations of the predictor as well as basically of the noise. Now for observations, I'm going to use small letters, and for random variables that are involved, I'm going to use capital letters in general, but I don't really follow this approach, so it's not that strict. Sometimes I basically mix it up to two. So I'm not going to distinguish between basically random variables and their corresponding empirical counterparts. Okay, so in general, but sometimes I do, so maybe on the slides I will follow this approach. But anyway, so you can, I mean, you can basically see what it is going to be. So that's that. Now, okay, let's assume that the sample size is going to be n. Okay, so n is a sample size. So I got basically n observations for the predictor as well as the response. I don't have the observation of the noise, and n is going to be, since this is a simple linear regression model, this is also going to be the number of observations of the pairs. So basically that giving you how many pairs you got basically for each. Okay, so you need to understand that these samples, both of the predictor as well as the response, are going to be connected. So the first observation of the noise, the first observation of the predictor and the first observation of the response are related to each other. You're not supposed to split them. Okay, so every pair, you know, is basically going to direct relate to a certain pair of observations for both for the predictor as well as the noise. You understand what I'm saying? So that's going to be very important here, guys. Now anyway, all right, so in this context, every observation is generated somehow, and then you need to understand that xi, let's say, is the ith observation of the predictor. So if I is equal to 1, that's going to be the first. If I is equal to 2, that's going to be the second. And if I is equal to n, this is going to be the last observation of the predictor. Let's assume that the sample size is already given. Okay, so if you have 100 observations, then it's going to be 100. If you have 200 observations, this is going to be 200. So depending on basically a lot of things, you know, for among others, how big your pocketbook is, because, you know, sampling costs money. So, I mean, you should understand this. But this is going to be given in this context. So whatever the N is going to be given. All right. Now, if you have basically the same mechanism also applies here for the response, you can also address, so I don't mind that basically if you say that epsilon I is the ith observation of the noise, but you need to keep in mind that the observations of the noise are not going to be observable. So if it's not there, you don't see them directly, let's say. I mean, they are there actually, but they're built in basically in the predictor, and sorry, they're built in the response, but you don't see them. All right, so you see those are there basically through the response, but they're not explicitly available in general. I'm not saying this is always true, but generally this is going to be the case. But I don't mind if you say, you know, due to the context that this is basically the ith observation of the noise, but you need to understand it's not there. All right, is it clear, guys? So even it's not there, I say it, but it's quite, you know, ambiguous, so it's not a good idea to refer to it as such. All right, guys, now this is basically, you know, addressing each sample observation. So there is random variables are involved that generate those, okay, and how you saw this in the previous setup. And now I'm going to look at the estimated version, because this is basically, you know, how it's expressed. The only difference is between the sample version, let's call it the sample version, this one, and the estimated version, is that for basically for the estimation, I mean, you don't know what the parameters are. So basically you need to address those as well. Maybe you should add that here, the parameters are not known in general. So unknown in general, okay, most of the time. So since they are unknown, let's say in practice, except for maybe you're simulating the data, then you know them, but other than that, it's not known, so you would need to estimate those. And for the estimation, I write basically A hat and B hat. So whenever you see a little hat, you know, up there, it's just going to referring to a corresponding estimation. Okay, so that is consistent basically all the time. And since you don't see the noises either, okay, so you need to also address basically that these observations are to be estimated. So you are estimating the observations of the noise, and the estimated observations are called residuals. Okay, so these are the residuals. So keep in mind, guys, there is a difference between residuals and noises. It's not the same. Okay, residuals are estimates of the noise. You understand what I'm saying? That's important. It's not the same because you don't see the noise in general, so you would need to estimate those. Okay, and this is what basically how it's addressed. So that's how you basically you can get, I mean, after a while, if you want to basically to explain, let's say, how this observation of the response occurs from the given observation of the predictor, and then everything else needs to be estimated. So you need to estimate A, B, as well as the residual to basically to get the response, and that's what you would need to explain. All right, so in this context, so this is how it works, guys. Okay, we were ignoring this, but in the last lecture, so yesterday I wasn't talking about that, but this is the context that I'm in, and you will need to understand that. All right, now I'm going to be basically consistent regarding the notation, so I don't basically drop these hats and whatever, and you should not either. But again, so this is basically what the context would be. Now, as you saw, this is the fitted value, right? So this is basically also the fitted value of the response, and I would need to address that as well. Okay, so we talked about that last time. You saw the fitted value is just simply basically the difference of the observed value of the response and its noise, or you can also look at the different perspective. The residual is actually the difference between the observation of the response and the corresponding fitted value. So that's the context I'm in. Okay, how would you calculate the fitted values? Simple is, after you estimating the parameters, you put into the equation, and that is basically the regression equation, by the way. So this is the regression line. You put in the observations of the predictor into that regression equation, technically speaking, and that's going to generate the fitted value. So this is how you would get those. We have addressed that yesterday. So lecture 3 is basically addressing that explicitly. So I was giving you an example to this, and then I would, first off, again, so from the sample pairs of the predictor and the response, I would basically estimate the parameters, and using these parameters, I would calculate then the fitted values, and after that, I would calculate the residuals, okay? You would not need to do this basically regarding the decompositions when it comes to the simple linear regression model. Why? Because the coefficient determination, and that's the main purpose why you would decompose these observations, is the square of the correlation coefficient, right? But the issue is this is not true in the multiple regression model. So for the multiple regression model, you would need to decompose every single observation of the response into two parts, into its fitted value and its residual, in order to calculate the coefficient determination. So you cannot do this when it comes to the multiple model, because in that case, whatever it is, you would need to calculate the empirical variance of the fitted value, right? And you would need to divide this by the empirical variance of the observation of the response, whatever that is, okay? And for the fitted values, you would need to calculate. You need to have the regression equation in the multiple model as well. So this is the only procedure how it works. So within the multi-dimensional framework, you would need to decompose that. You are, implicitly, okay, so you're not doing this, the computer does that. But if the computer wants to basically calculate the coefficient determination of a multiple linear regression model. What is a multiple linear regression model? I forgot to mention this. A multiple linear regression model is a regression model where you have multiple, so at least two explanatory variables, at least two. Okay, so then you have three predictors because the constant is also considered to be a predictor. All right, so you have basically three parameters, at least. Okay, so at least two explanatory variables. Okay, multiple. All right, so there is no way to bypass that anymore. But this equation is also true within the simple linear framework. Okay, so that is basically true for both the simple and the multiple linear regression model. But the issue is for the multiple linear regression model, you cannot bypass calculating the coefficient determination. You cannot bypass the decomposition of the response. And for basically for the simple linear regression model, you can, because for the simple linear regression model, as I mentioned yesterday, the coefficient determination is simply just the square of the correlation coefficient. So you can just basically do that. You don't need the decomposition. This is clear, guys, okay? So, but these statements are still true regarding basically the multiple model as well. I'm not going to talk about the multiple model. I will give you, let's say, a little case study, and then you can watch how I was basically setting up the multiple model, if you like. So you would need to understand this. I don't have time to talk about these things, in that detail. Actually, we could also spend a whole semester talking about the, the multiple linear regression model from A to Z. But again, I cannot do this. So we need to talk about time series also, right? But these are the tools that you need. Now, yesterday, okay, lecture 3, we have also addressed what the residual variance is. I'm talking about, if you say residual variance, this is the empirical variance of residuals. So this is the empirical variance of the residuals, okay? And the empirical variance of the residuals is calculated how? You might remember that. It's calculated from the mean of the squares minus the square of the mean. That's always the formula, right? Mean of the squares minus the square of the mean. Now the mean of the residuals is going to be 0. Okay, so the mean of the residuals is 0. You might remember this from last time. So the empirical variance of the residuals is just going to be the mean of the squares. That's it, okay? Because again, the square of the mean is going to be 0. So if you subtract 0, you could skip it. Anyways, okay, so the mean of the squares, how would you basically get that? So you do basically first the sum of the squares you have the residuals. You need to calculate the residuals first from basically from the difference from the observation of the response and the fitted value, all right? And then you square those, you sum them up from the first to the last observation, and then you divide it by the sample size. If I say division, and of course I mean basically multiplication by the inverse. So you divide basically the sum of the squares by the sample size. The sum of the squares is calculated from, I mean, each residual is calculated from the difference between the response and the fitted value, so that's similar. And you saw that this is basically, you know, the sum of the squared residuals, for which I use the acronym RSS. Okay, so RSS, sometimes it's also explicitly written down like this. So RSS, for example, I've seen this, I remember correctly, eViews and some programs just write down RSS. You need to know what it is. So that's the most important, basically, sum of squares here that is involved, but that's just basically the sum of the squared residuals. I'm going to address it. That's it. Okay, so the mean of the squares, because the square of the mean, I mean, you could also address it, the square of the mean is 0, so, but that's the variance. All right, is it clear, guys? So you need to address basically what RSS is. Now, if you are within the simple linear regression model, you can get the RSS from the coefficient determination. So usually, if I'm within a simple linear regression framework, I need to address it. Okay, I did this last year. So last year I was, you know, I was the one lecturing statistics for, you know, the bachelor's course, and then that was an exam where you would have the coefficient determination and then, or a correlation, and then you would need to calculate that. So from the correlation, so that's the approach. From the correlation, I calculate the coefficient determination of the regression. And since the coefficient determination is equal to 1 minus RSS divided by TSS, TSS is basically n times the variance of the response. You might remember that. So that's the way to extract basically RSS from this expression. Okay, so here it is, and then you would basically extract that, and then you simply divide it by the sample size, so you would get that. But that's not what I did. But I can only do this in a simple linear regression model. But in the multiple linear regression model, I cannot do it, so I have to calculate the residuals in order to get basically RSS, because there is no way to bypass that within the within the multiple linear regression framework. Is this clear, guys? So again, that's why I was addressing it like this, explicitly from the residuals, because that can be done in every case, whether it's a simple or a multiple framework. Now, what about basically the estimated variance? Because the issue is, this is not basically unbiased. So this estimator is not unbiased. You need to correct it. So there is the bias correction that I'm addressing here. And how would you do that? Now, this is done in the simple linear regression only. So you would need to basically to calculate the sum of the squared residuals. So there is no way to bypass that. So again, you need to calculate RSS. That's, you know, that's the same sum that is consisting of, but it's not divided. But I mean, from the first observation to the last, so of course you would need to sum up, but it's not divided by the sample size, it's going to be divided by the degrees of freedom. And the degrees of freedom within a simple linear regression model is going to be n minus 2. Why 2? Because you got two parameters to estimate. First, I mean the slope, and then second, the intercept. Two parameters are involved. So if you want to address basically the degrees of freedom, the F, okay, the F is the number of observations minus the number of estimations that you would need to rely on to get basically, in this case, the variance estimation. Now the variance estimation is, you know, you need to understand variance with respect to what, and the variance with respect to the regression line in this case, because this is what the noises are doing. Okay, so that's basically, you want to estimate the variance of the noise, not the residuals, guys, the noise, because the noise is the random variable, so you want to estimate the variance of that, and this is done by basically adjusting this estimation by the degrees of freedom. You've seen this, right? So in statistics, I'm teaching this all the time. So then, because this estimation or this estimator is not unbiased, unbiased is the term Erwartungstreue, that's the German expression, okay? So you heard about that. So if I say unbiased, that's the term, all right? Unverzerrt, that's also another one, but unverzerrt, Erwartungstreue. All right, so that's that. Now, again, so this is quite similar, right? So everything else is going to be the same. So you need to basically divide RSS by the degrees of freedom in order to get that. And that estimation is not going to be unbiased. So that's going to be unbiased, right? So this is biased, right? That is biased, but that is going to be unbiased. I'm also addressing that as well. All right, guys. So yeah, and degrees of freedom, again, simple linear regression is going to be n minus k. In a multiple linear regression, so if for the multiple linear regression, you need to calculate the residuals using the same approach. Looking at you need to estimate the regression equation first, and then you calculate the fitted values, and then you calculate the residuals, and then the degrees of freedom within the multiple linear framework is going to be n minus k, where k denotes basically number of predictors, including the constant. Okay, so you can say n minus, if you're kind of confused, n minus j minus 1, and j is the number of explanatory variables, okay, without the constant. So j is basically addressing the number of explanatory variables. Within the simple linear regression, okay, we have being as j is going to be equal to 1 within the simple linear regression, right? So we have just one explanatory variable, but keep in mind the constant is also considered to be a predictor here for the response. All right, so that confuses people. So that's the reason why basically predictors and responses, predictors and explanatory variables are not the same, but people tend to use them synonymously, unfortunately. Anyways, is this understandable? Now, you should have seen this basically. I remember, lecturing it last year, so maybe you have seen that before, okay? And what you need to know is how to calculate basically corresponding standard deviations. Now, if you take the square root of each, which I'm going to or have done, okay, you're going to get the standard deviations. Now, the standard deviation that is obtained from the corrected variance estimation is called standard error of regression. This is actually the second most important output that you would see within the linear regression, guys. Okay, so this is the corresponding standard deviation that you would get from the variance estimation. That's it. Now, this is the mean predicting error of the model, or the estimated standard deviation, right? So because this is an estimation, by the way, which is unbiased. So that's the unbiased version. Is it clear? Okay, so you can also refer to that as mean predicting error or the estimated standard deviation of the noise. Okay, so standard error of regression is the estimated standard deviation of the noise. Okay, so this is basically interpretation. And the corrected version of it, of course. You can use that as an estimator too. So nobody's basically telling you what to take for estimation. But if you take the residual standard deviation as the estimation for the standard deviation of the noise, then this is not going to be unbiased, whereas the former is. You understand that, guys? So that's basically the issue, all right? Again, standard error of regression I think after the coefficient determination is the second most important output that you will have on a linear regression model. Keep in mind, guys, and what is also important is that it has the same units as the response. All right, so let's say if basically, if the response or the units are, let's say, given in some sort of euros or whatever, okay, or dollars, and the standard error will be also in the same unit. Okay, so that will be also euros as well. Okay. In contrast to basically to the coefficient determination, which is always a percentage. Okay, so that's always going to be a ratio. Okay, but that has the same unit. All right, is it clear? Okay, so that should be important basically to note. Okay, and that basically give you the error or the prediction error basically of the model regarding in units of the response. That's it. Okay, so because the standard deviation is literally that. So you deviate from the regression equation, which means that you have an error. Sometimes you're above, sometimes you're below the regression equation, for both for multiple as well as basically for the simple linear model. Now, here in this case, again, I'm going back to the variances. Okay, so again, these are the standard errors or the standard deviations, right? And then you have the variances. If you take away the square root, so under the square root, these are the expressions. And then I'm going to address some properties that they have. Okay, so one property is, and I talked about this already, so if sigma squared is basically the variance of the noise, so let's assume that it is the case, inconsistency with your second assignment, by the way, so I was basically addressing that. Technically, it's the conditional variance, but it will be, if I'm not saying it is the unconditional one, but let's say if it is the unconditional one, you would need to show actually in your second assignment that if basically conditional variance, so given the predictor is equal to sigma squared, then the unconditional variance is also going to be sigma squared, so I can tell you about it. Anyways, so, but let's start from here. So I'm not saying this is an assumption, I'm saying if I start from here, because I didn't talk about, the assumptions of the model. So if the variance, the unconditional variance of the noise is sigma squared, then you could also check for the corresponding random variable. So then, of course, every estimation is also a random variable. So within that context, if I take the expectation of the standard, or the square of the standard error, then you will find that this is going to be equal to the variance of the noise. You understand what I'm saying? So that's the issue here, and that is not going to be unbiased. So basically the latter, when you look at the variance of the residuals, is not an unbiased estimation here for the variance of the noise. But it's going to be asymptotically unbiased. All right, so because there is not much difference. So when a sample size is large, there is not much difference. Okay, so in this case, degrees of freedom are n-2, okay, and basically within the limit of that is going to be equal to n of course as well. So if you just basically compare that, so if you take the degrees of freedom, dividing it by the sample size, you will find that this will basically converge into 1 as the sample size increases. So as the sample size increases, there is not much difference regarding the relation between, or the ratio between degrees of freedom and the sample size. Okay, so let's say you got 1 million observations, you would not even notice whether you would correct the estimation regarding the variance of the noise or not. Okay, so for large samples, there is not much relevance to it. Okay, is it clear? All right, so I think you've seen this before, but I wanted to make it clear. So yeah, this is what it is. Again, and yeah, so that's that. All right, so this is something that you don't need to show, by the way. It's not difficult to show, you trust me on this, especially for the multiple model, but you need to have so-called projection matrices to do that. So to do it very elegantly, this requires so-called projection matrices and decompositions of those, regarding eigenvalues and eigenvectors and all that stuff, but I'm not going to address that, okay? So so-called idempotent matrices are involved. So I do this in my PhD courses, and then you could basically have seen, you see the proof in a relatively elegant way. Within a simple linear regression, it's also easy. You can just simply, standard, this is a standard approach. Just, look at the expectations, and that's going to be. Anyways, but I'm not going to address it. It's a little bit, I'm not saying it's difficult, but it's time consuming. But within a multi-dimensional framework, it's this can be done very relatively elegantly. So, but I'm not going to do that. Anyways, so let's go back to the example and let's calculate basically the standard error of regression here from the example. Again, so please review basically last lecture how I was basically getting these samples. But again, the things that were given were the sample of the predictor and a sample of the response. These are the things that are given. From that, I would calculate the estimations basically for A and B, and looking at that, so from here you would calculate the fitted values, right? And from here you would calculate the residuals. So this is the mechanism, right? Please review this from last lecture. You'll see how I did it. Okay, now I want to start from here, and I want to calculate the sum of the squared residuals, even if even that is not going to be necessary, because I was calculating the variance of the residuals already. So if you take the variance of the residuals, okay, so if you want to basically get RSS, you would simply just take the variance of the residuals, right? And you would simply just multiply it by the sample size. You can skip it because we have done that already. But I'm going to start from here. So I would take basically the residuals as they are. So, and then square them, and then, you know, sum them up. So that's it. Okay, as it says for itself, sum of the squared residuals is the sum of the squared residuals. God damn it, what else? All right, so that's it. Anyways, so I got 3.15 if I did it correctly, and then from here you can calculate the standard error of regression. If you divide, and that's simple, if you divide basically the sum of the squared residuals by the degrees of freedom, and then you take the square root of that, and that's going to yield the standard error. So, and yeah, I got the following expression, so you can see what it is. Okay, 1 by the degrees of freedom. If it's the multiple model, then the degrees of freedom are going to be n minus j minus 1, where j denotes basically the number of explanatory variables. In a case study, you can look that up. Okay, so you see how this works, and that's how it's done. And for the residual sum of squares, you need to have the residuals, of course, within the multiple linear framework. Within a simple linear model, you could skip it. Anyways, so that's what you got. Okay, so then you got basically the sum of the squared residuals divided by the degrees of freedom, which is 3. So you have 3 degrees of freedom. It's not a lot, by the way, but I need to basically use a simple approach. And that is equal to the square root of 1.05. Now that's the exact value. I was not able to construct basically a model or observations to a model where from given predictors and well as responses where this goes fine. So again, that's the first time I would need to rely on approximations, as you see. But again, so if you have an idea how to get a sample like that, where everything is basically just, you know, use this accuracy. Maybe the correlation was a lot of work, even that. So I remember the correlation was 0.75. So this is exact value, but here the first time I would need to route. Anyways, okay, you can take that to be the exact value instead if you like, but I was not able to generate a sample like this. Anyways, so but that's just, you know, for teaching reasons, basically for explanatory reasons. Anyways, so the standard error of regression coefficients, which I also want to address. Okay, for each, for both for the slope as well as the intercept, you would need to have the standard errors for that. So you need to multiply the standard error of regression by something to get basically that, and that will give you the prediction error of the slope. Okay, so if you say, let's say, if I increase x by 1, and then you need to increase by, you know, to say in a regression line, basically to by 0.09, it was like that. Okay, so that has basically also a prediction error in it. Okay, because just because you increase x by 1, it doesn't necessarily mean that y is going to increase as well. So this is going to deviate, and the question is how, and that's going to be expressed by the corresponding standard error of the slope. Okay, so that's not the slope, guys. This is the standard error of the slope. Okay, but I was just using that one. All right, so that's not the slope. That's the standard error, and that's going to be, you can also say this is the prediction error of the increase of the response, not the response itself, as just was the prediction error for the standard error of regression. So this involves basically the standard error of regression, as you see. All right, so the standard error of regression is the prediction error of the response, whereas the standard error of the slope is the prediction error of the increase of the response. If you increase x by 1, then how would basically, you know, the prediction error of the increase of the response would be, and this is basically addressed by that. Do you understand this, guys? So again, now how is the formula generated? This is not something that I'm going to talk about here. Okay, so you would just need to know this. Okay, and then you can also calculate the standard error of the intercept if you like, but that's not very common. So because you want to test the significance of the predictor and not necessarily the constant, right? So you want to test the significance basically of the explanatory variable most of the time. Okay, so I mean I'm skipping that one. Okay, so because I'm interested in basically the prediction error regarding the increase of the response. If x is increased by 1 unit, you know, how would basically the prediction error would be. But again, you can also address the standard error of the intercept as well. The standard error of the intercept is basically the estimated standard deviation of the, basically of this estimation, namely the intercept, right? And this is also the estimated standard deviation of the estimation here for the slope. All right, so this is another interpretation basically for these expressions. Every software does that. So every software is basically displaying the standard errors of the corresponding regression coefficients. Okay, and if you want to calculate the so-called test statistics, which is, you know, as a following work, okay, all you would need to do is taking those standard errors, okay, and divide basically the regression coefficients by it. This is also displayed by every program, okay, and most of the time you test the null hypothesis that the corresponding parameter is equal to 0. So that's why I was also adding 0 here to this expression. So minus 0 is, of course, is not going to be an issue. So whatever you subtract 0 from is going to stay that way. But if you have a different null hypothesis, right, then you can simply just change that. So that's why I was including it here. Is it clear, guys? And that is also true for the intercept as well. So if you test the null hypothesis, let's say that the, whatever the reason might be, that basically that the regression coefficient by the slope is equal to 1. Okay, we're going to test this when testing stationarity sometimes. Okay, you simply replace 0 by 1 and that's it. But I'm not going to do that. But that's not a test statistic actually, because test statistic regarding the significance of the model. So we test the significance basically of the explanatory variable in most of the time. So that's basically I was addressing that this way. All right, so depending on what the null hypothesis is, you would get a different test statistic. But again, so that's it. Now, regarding the distributions, you need to have an assumption that the noises are normal. Okay, so you cannot, if you don't have the normality regarding the noise, you can only address the distribution asymptotically. Okay, so you can address the distribution asymptotically. So asymptotically, it will be standard normal. So this is written like this. So if this is not there, then this will basically, due to the central limit theorem, again, so, but under the null hypothesis, this will converge to the normal distribution, or the standard normal distribution, in distribution as basically the sample size increases. Okay, so as you might know, central limit theorem, you heard about that. But again, in basically, so you can bypass this thing regarding it, but if you assume the noise is to be normal, why not actually? So why not? Okay, from the normal distribution, right? Then this will be following the t distribution with n-2 degrees of freedom, and both of them actually. So this is the representation for it. So both test statistics, both for the intercept as well as the slope coefficient would follow the distribution. The t distribution, by the way, with n-2 degrees of freedom, where n is, of course, the number of observation pairs in a simple linear regression model. And, of course, within the multiple linear regression model, n denotes the number of observations of the response. Is it clear, guys? So I think you heard this. Again, so the t distribution is applied, but only if the noises are normal. So only in that case. Okay, so if you can make that assumption. If the noises are not normal, then basically the test statistics do not follow the t distribution, but for large samples, they would basically, you know, converge. I mean, the distribution basically of those would converge to the standard normal distribution. I mean, it kind of, you know, the t distribution is also converging to the standard normal distribution itself if basically the sample size increases, right? So this is how it's readily expressed. Is it clear? So again, the t distribution has actually for small samples, it has a relevance, but you know, but you can only use it if you make the assumption regarding normality of the noise. If not, then you need to use the central limit theorem. But again, that for large samples at least, you know, so you have to have large samples if to bypass that. But if you have large samples, you just use the standard normal distribution instead. So that's it. All right, and especially for financial data, right? So you have large samples, right, regarding finance or whatever, capital markets and stuff like that, especially with high frequency data. All right, so nobody does the t distribution, but again, so this is all I mean, that is the corresponding p-values regarding hypothesis testing are calculated like this. Anyways, okay, so I want to basically address how to make a test decision based on that. So you need to calculate the corresponding test statistic, and you would reject the null hypothesis, whatever the null hypothesis is. So most of the time it's going to be the significance of the corresponding parameter or the significance of the explanatory variable attached to it, whatever it is. So you would reject it if and only if the absolute value of the test statistic is greater than the 1 minus alpha half quanta of the t-distribution with n minus 2 degrees of freedom. So within the multiple linear regression, you simply replace degrees of freedom by df, okay, whatever df is. So again, in the multiple linear regression, n minus k, where k denotes the number of predictors, or versus n minus capital J minus 1, where j denotes the number of explanatory variables. You have the explanatory rule. So let's say you have the explanatory variables plus the constant would give you basically the number of predictors within the model. Okay, so keep in mind the constant is also considered to be a predictor as well. Is it clear? All right, so that this is something that you would need to replace. Okay, so the more observations you have, okay, the lower, the more explanatory variables you have, the lower the degrees of freedom are going to be. All right, is it clear or is it smaller? Anyways, so this is basically how you can apply the same approach within the multiple linear regression framework, but you will need to also consider that the test statistics are calculated differently, so the formulas would not be the same. Anyways, all right, so let me just basically do that one. So I'm going to calculate basically the standard error of the slope, okay, step by step. So again, please review this from last lecture. This is the empirical variance of the predictor. So of this, basically of this sample, sorry. So the variance was 100, and you have already had the regression coefficient with 0.09. And that was calculated from the, so regression coefficient one, calculated from the empirical covariance divided by the variance of the predictor, right? So that's what we have done. And empirical covariance, as I remember, was 9. Okay, from last. Now, the standard error of regression, we already addressed that as well. I'm not going to do that again. Then the standard error of the slope using this formula, so that's a formula, it's simple actually. You simply use the standard error of regression, which is there, and then you multiply it by 1 by the square root of the sample size. Now the sample size is 5, you got 5 observation pairs, so this is going to be it. And then you have times the standard deviation of the predictor. Now, the variance of the predictor is 100, so the standard deviation of the predictor is going to be 10, because that's the square root of that. So you're going to see 10 in the denominator, which is basically the square root of 100. So I was not bypassing that. This is basically the exact value. I was not using approximations here. Okay, so because I take that and I'm going to calculate the test statistic. I don't know what basically the square root of 21 by 100 would be. Somewhere between, I don't know, 0.04, 0.05, somewhere around that. It doesn't really matter, so it's basically that. Okay, but that's basically the mean prediction error regarding the increase of the response if x is increased by 1 unit. Okay, you cannot say if x increases by 1 unit, then the response would increase by 0.09 units, because that's not certain. Okay, so you can, but it's not necessarily the case. To stay in a regression line, you need to basically to have an increase of 0.09, but usually you don't say it on a regression line when it comes to observations. Okay, all right, so that's the mean predicting error of the increase of the response if the predictor is increased by 1 unit. Okay, so that's that. This is the standard error of the slope. I mentioned that before. Now, the test statistic is done by just simply dividing the estimate by the standard error, or by its standard error, let's say, and this is what I did, and the approximation is going to be 1.964. All right, so that's basically the proxy here for that, or the exact value is the square root of 27 by 7. All right, okay. Now, this is the test statistic. There is no interpretation regarding the test statistic, so you cannot interpret the value of the test statistic only in the context of the t-distribution, because that's something that I'll need to look at. The critical value to which I basically compared it to is going to be the 1 minus alpha half quanta of the t-distribution with n minus 2 degrees of freedom. Now, if alpha is the error probability, which is 5%, I'm going to use 5% in most of the cases, when actually in most empirical studies, most people choose 5% to be the error probability. Error probabilities, you might remember the probability of type 1 error, right? Type 1 error means rejecting the null hypothesis and it turns out to be true. Okay, so given the null hypothesis is true, the probability that is rejected is at most 5%, or should it be at most 5%? That's what you need to specify. So you need to specify what the error probability is in advance. Don't make it too small, because if you decrease the error probability, right, which means that you decrease the probability of type 1 error, then you also increase the probability of type 2 error, okay? If you don't reject the null hypothesis very often, then it could be the case that it turns out or it could turn out to be the case where you should have, or, you know, so if type 2 errors, of course, means that you do not reject the null hypothesis, but it turns out to be false, all right? Okay, so you're supposed to make it small, but not too small, so regarding the error probability, because then you increase the probability of type 2 error. Anyways, so I need to look at the 0.975 quantile of the t-distribution with 3 degrees of freedom, so you 97.5% quantile. The 97.5% quantile is a value that is not exceeded by 97.5% of the distribution. And how would you get this? I would also providing you a distribution table regarding the t-distribution, so you can check it out there. You go to basically to the row where you have 3 degrees of freedom, and the column where you have the 97.5% quantiles, and there you would find 3.1824 for the basically for the 97.5% quantile of the t-distribution. Got that, guys? So you probably remember this from statistics. Okay, and then after that, you just need to make sure, I mean, how would you make your test decision? You reject the null hypothesis, as again mentioned before, if and only if the absolute value of the test statistic is greater than the 1 minus alpha half quantile of the t-distribution, which was 3.2, let's say, okay, approximately, but the test statistic was, as far as I remember, 1.96. So if you compare that to the test statistic, which was 1.96, then you find that the absolute value of the test statistic is not greater than the critical value, so therefore you would not reject the null hypothesis in this case. So then you would say that although the correlation, you might remember, was 0.75, which turns out to be large, okay, the parameter p is not significant, statistically speaking, and the reason for that is, of course, because the number of observations is small. So even basically, you know, you have to have a, you know, greater correlation in order to basically establish significance between the two variables. If you just have 5, okay, so that's not going to be enough, okay, so depending on this issue, all right, but that's the reason so why this correlation does not turn out to be significant. Is this understandable, guys? Okay, so that's basically how it works. Now, you know, I want you also to understand how basically decision making or the process would be. That's the density of the t-distribution. It kind of resembles to that of a normal distribution, but you know, you have basically a larger type of kurtosis here for that, but it's not going to be important, guys. 3.2, let's say, okay, so 3.2 is a 97.5% quantile, which means that 97.5% of the distribution is not greater than that, okay, so the area from minus infinity to the 97.5% quantile is 97.5% by definition, right? And this is basically 1 minus alpha half, because alpha is 5% then, so keep in mind I'm always using 5% error probability here. Now, if the pink area is 97.5%, then the little orange area, which is to its right, must be 2.5% then, which turns out to be basically half of the error probability, of course, right? Because the two areas sum up to 1, which it does basically for every density there is. You might know this, right? So if this area on the right is 2.5% of the total area, then since the distribution is symmetric with respect to the y-axis, so the y-axis is here, guys, okay? It's not there. It's basically in the middle, because here you have 0, right? So if the distribution is symmetric with respect to 0 or with respect to the y-axis, then the area right to 3.2 is just as large as the area left to negative 3.2 approximately, all right, and this is also going to be 2.5%. So if you cut off 2.5% on the right and 2.5% on the left, you're left with 95% basically in the middle, and 1 minus alpha is the confidence level, guys, so this is going to be, of course, 95% of the distribution. If the test statistic falls into that range, which it does, or which it did, because this is 1.964, this is between negative 3.2 and plus 3.2, which is basically covering 95% of the distribution, then of course you would not reject the null hypothesis, because this is the acceptance range for the test statistic. You understand? So, and of course, if this is the acceptance range, then its complement is going to be the rejection range. So the rejection range is the union basically from the interval from 3.2 to plus infinity and from minus infinity to negative 3.2. So the union of that is going to be the rejection range. If that statistic falls into the rejection range, then you would reject the null hypothesis, which we don't. So since it's basically inside the acceptance range, we don't reject the null hypothesis. Is that clear, guys? Okay, so this is actually how this works. Now, we want to also address what the smallest error probability would be by which we would reject the null hypothesis. So that's going to be the p-value. So you can use the term smallest, but it's not correct. Okay, I'm going to tell you why. Because that's not going to be the minimum. That's going to be the infimum, and there is a little difference basically between the two. So again, so let's say if the p-value is alpha star, again, the p-value is an error probability, which I'm going to address. And this is also, I think, the most important, basically, I mean, when it comes to hypothesis testing. So not regression only, but when it comes to hypothesis testing, that's something that you should always look for. So check, you know, what the p-value is when you run a basically computer program, because that's the easiest way to make test decisions. The p-value is the smallest error. I mean, I say smallest, but it's not true. So let's say this is an infimum, right? Infimum of basically of all error probabilities, you can say the smallest. So let's say I'm replacing infimum by the minimum, although it's not true. So the smallest error probability for which the null hypothesis is rejected. I'm not sure if you know what the term infimum or that means. You haven't known. I mean, this generalizes basically the concept of a minimum. So let's say, for example, I'm looking at the interval from 0 to 1, okay? And I'm looking at the minimum, right, of this interval. The minimum of this interval is, of course, 0, because that's the smallest number that this interval has. But let's say you're looking at the minimum of an open interval, and you have an open interval which basically does not include 0. I mean, it could include 1, but it does not include 0. That does not exist, okay? So does not exist, okay? Because it has no minimum. Whatever you come up with a minimum, you can always find a number which is even less than that from this interval. You understand that, guys? So this is an issue, but the infimum does exist. So this is basically generalizing that concept for open intervals, okay? If basically that's not there, because the infimum, okay, so let me write it like this, is or does exist, okay? So that's basically generalizing it, which is 0. Okay, so just replace basically term infimum by the minimum, and then you know what's up. But you need to know that infimum is basically the, let's say, the generalization of that concept for open intervals, to put it basically in simple terms. All right. So infimum is the term. This is the greatest upper bound, greatest lower bound. Okay, of the interval. All right. The greatest lower bound. So you're looking at basically from the bottom. Is it clear what the term infimum is? Because keep that in mind, whatever the p-value is, so let's say the p-value is, let's say, 3% or something, okay? This is not an element, or say, so 3% is not an element of this set. So I'm talking about this set here, okay? So let me write it down. So the p-value itself, okay, let's say, which is equal to 3% in this case, is not an element of the corresponding set to which is referring to. Okay, so this set containing basically all alphas, where you would reject basically the null hypothesis. This is not an element. That's not inside. So this set has no minimum, guys. If it was basically equal to it, then it would be, but that's not the case. All right, so you're looking for the greatest lower bound of all error probabilities where you would reject the null hypothesis, but most people don't understand the concept of the greatest lower bound. So you can say smallest error probability, I'm fine. All right, although it has no minimum, but you need to keep that in mind. Is it clear? All right, so that's that. I'm going to address it explicitly what it will be. Now, in this case, if the null hypothesis claims there is no significance regarding the parameter for the slope, okay, then you would reject the null hypothesis if the absolute value of the test statistic is greater than 1 minus alpha half quantile of the t-distribution with n degrees of freedom. So if you do that, or let's say if this happens, then you do reject basically the null hypothesis, as we mentioned before, okay? So if the test statistic has an absolute value which is greater than 1 minus alpha half quantile of the t-distribution, now if alpha is equal to 5%, it was not the case. So we would not reject the null hypothesis, right? So that's not part of that. Anyways, but you collect basically every single error probability for which it does, and you take basically, let's say, the smallest, okay? So I'm addressing the smallest error probability for which you would do reject the null hypothesis. I'm going to talk about it so you see how it's done. Basically, I mean, looking at basically from the distribution, in order to reject the null hypothesis, the test statistic must be outside the acceptance range, which is not the case. It is inside the acceptance range. This is the acceptance range here. So if you want to basically to get that done, you need to increase the error probability. So we're going to increase the error probability until you would basically, or for the first time, you would basically reject the null hypothesis. You understand what I'm saying? So the area can be greater that you cut off from the left to the right, and you would still, you would still not reject the null hypothesis. So you would need to increase the error probability basically to be able to do this, because as long as the test statistic is inside the acceptance range, the green range, right, you're not going to reject the null hypothesis. So we need to basically increase the error probability. You see how I do it? So I basically increase until the point basically where the upper bound of the corresponding confidence interval, let's say basically for the test statistic, because that's literally what it is equal to the test statistic itself. Okay, so until basically the 1 minus f a half quantile of the t-distribution is identical with the test statistic, because then you would still, I mean, for the first time, you would be able to get the null hypothesis rejected at least. You understand that? And so therefore, the p-value is twice as large as this area here right to the test statistic. So you need to calculate this area. Okay, it was blue, so sorry. I would use that one. So you need to calculate this blue area, multiplying it by 2, and then you would get the p-value. And how would you get basically the blue area? The total area is 1, and then you would basically subtract the, I mean, let's say you have the CDF of the t-distribution, which I don't know, but capital F, at point 1.964. Okay, so you put in 1.964 into the cumulative distribution function of the t-distribution, and then you subtract that from 1, and that will be basically half as large as the p-value, and then you multiply it by 2. Okay, so the p-value is twice as large as this little blue area to the right of the test statistic, guys. Do you understand this? This is how it's done. Okay, so then you don't need to, invert, these distribution functions and none of that stuff. So you can solve this issue actually graphically, and this is basically what you would do. And this is what I did. So I was calculating the p-value for that. Okay, check it out. So this is where we would start it. The smallest, let's say the smallest error, I put this in quotation mark, the smallest error probability for which a null hypothesis is rejected. And if you break into that, which I'm not going to do, okay, if you break into that, you'll find that if basically capital F denotes the CDF, so the cumulative distribution function of the t-distribution, with n minus 2 degrees of freedom, this is going to be twice as large as the area right to the absolute value of the test statistic. So even if the test statistic is negative because the distribution is symmetric, you could solve this issue by basically just, doing that. Is it understandable, guys? Okay, so then you would reject the null hypothesis, and this is what I did. So I was calculating it, okay, but that's, so after that, when you calculate the p-value, which is done by the computer, okay, so, but again, this approach is only true if the null hypothesis is like that. So if you have a two-sided test, then you need to multiply basically the area right to the test statistic by 2. Okay, so right to the absolute value of the test statistic equals positive. Okay, if it's a one-sided test, then that's not true. Okay, so then you need to be doing something else. But that's the most common test, so this is within the regression analysis, so that's what I'm basically addressing. After you calculate the p-value, the test decision is going to be extremely easy, guys. You reject the null hypothesis if and only if the p-value, is less than the error probability. So most of the time, I use 5% for the error probability. So if the p-value is less than 5%, you reject the null hypothesis, period. Okay, I could teach a 12-year-old, applying this. Okay, so just look for the p-value. If it's less than 5%, reject the null hypothesis at the 5% level. That's it. Okay, so That's it, okay? I mean, that's what I'm also going to do, and you can see that for yourself. So I was calculating basically this area. It turns out to be approximately 7.2%. It looks larger than that, but keep in mind, guys, that the scale is different here than on the x-axis, okay? So the distance between, let's say, between these 2 points, okay, has 2 units, okay? And 2 units are not proportional basically to that one. So this area actually looks larger than it is, okay? But it's just 7.2% approximately. So you take that, so right to the basically test statistic. This is something that you cannot do with the distribution tables, because distribution tables in general, let's say, because distribution tables related to the t distribution only display the quantas but not the areas, okay? But you don't need to. The computer does that, so I was myself using the computer to calculate this. Then I was multiplying it by 2 to get the p-value, which is approximately 14%. Okay, so since the p-value is 14%, is greater than 5%, don't reject the null hypothesis. Okay, so again, please remember, you do reject the null hypothesis if and only if the p-value is less than your predetermined error probability, which is 5% most of the time. And since basically the p-value, which is approximately 14%, is greater than 5%, which is the error probability, I don't reject the null hypothesis at the 5% level, as basically which was consistent to the approach that I did in the previous part. Is it clear? Okay, so that's the mechanism that is here, and you should know this, so I wanted to make sure that you do, although it's basically relevant in statistics. But some people, I mean, my experience is that most people don't really understand what this is about, so I wanted to have that reviewed, because again, the tools, what we do in this class are going to be the same tools that we use also for time series, but for time series we use it differently. So you're going to see, because there are some issues involved regarding time series, so you could not just simply use these things. We need to talk about that actually. Okay, so I'm going to explain one by one what this is going to be. All right? Okay, you kind of looking, I mean, you're confused?
Yeah, I don't really understand, because I thought we were looking for alpha being 0.051.
0.0 what?
I thought we were looking for alpha star being bigger than alpha.
I mean, 14% is greater than 5%.
Oh yeah, you're right, being smaller.
Yeah, so you reject if it's smaller, but since it's bigger, I don't. Okay. Right? So I mean, this implies if I say if and only if, this means if it's not smaller, then you don't reject it. You understand what I'm saying? So if basically x is equivalent to y, then the negation of x is going to be equivalent to negation of y as well. You understand? So if it says if and only if, okay, this implies that if it's not smaller than the error probability, then you don't reject it if it's not smaller, because 14% is greater than that. All right? Is it clear? So that includes basically that one. All right. So yeah, if the p-value was less than 5%, then I would reject it, but I don't in this case. Is this understandable? So you need to make it bigger to be rejected, but that's too risky. So you can say reject the null hypothesis, but if you reject the null hypothesis, your type 1 error is going to be, 14%, which too risky. You understand what I'm saying? Right? At least from this perspective. But you can do it. I mean, when you go to a casino, you know what I'm saying? But I don't want to go into that. Is it clear, guys? Now, the next assignment, not the second one, the third assignment is going to be about the linear regression with time series. So I want you to run a linear regression with a specific time series. I'm going to describe how to. Okay, so even the simple linear regression can be applied under certain circumstances when it comes to time series, and you would need to run it. So I'll give you, let's say, fictive data. Everybody is going to get a different data. Okay, so everybody needs to do, need to run a different regression. So again, so the only things that you would need: arithmetic means, variances, covariance, correlation maybe, regression coefficients, standard error, test statistic. Yeah, that's fine. P-value, too complicated, but maybe you could do that. I give you that a bonus. So if you figure out how to calculate p-values from Excel has a function where you can use the cumulative distribution function of the t distribution. Okay, so if you can do that, I'll give you that a bonus. Anyways, so that's going to be your third assignment, guys. Any questions related to that? So this fourth lecture. Now, next week, okay, on Wednesday, we're going to start by looking at time series finally. So, but I need to have basically just 2 weeks to.
Isn't there a attack on Wednesday?
Excuse me?
The first May.
Yeah, no, you're right. There's no lecture on Wednesday. On Thursday, there's lecture. That's correct. I forgot. Okay, but on Thursday you need to come. You know. So again, okay. Then I'm not going to give you an assignment then, or maybe I do. I don't know. Maybe I do. Okay. Yeah, you need to work. So you got a lot of things to do. All right. So that is intense. I know, but there is no test. Okay, so no exam. Basically, when the course is over. That's the advantage. So you can prep basically for the rest of your stuff. Anyways, okay guys, so that was it for today. Thank you very much. Take care.